Science seminar, and we are delighted to invite Professor Phanindra Tallapragada to introduce his interesting work on constraint passive mechanics and embodied sensing in fish-like swimming. So before the presentation, I will give a brief introduction of our speaker. Professor Phanindra Tallapragada is an associate professor in mechanical engineering at Clemson University. He got his PhD in engineering mechanics and master's degree in mathematics from Virginia Tech in 2010, and did postdoctoral research at the University of North California, Charlotte. He joined Clemson University in 2013. His research interests are in dynamic systems and bio-inspired locomotion related to terrestrial motion, fish-like swimming, and low Reynolds number swimming. So as usual, our presentation will last about 45 to 50 minutes. And as told by Lisha, please do not interrupt our speaker during the presentation. And after that, we will have a question and answer session. So now I will leave the time to Professor Phanindra Tallapragada. Let's welcome.
Thank you. Thank you for the kind introduction and the invitation to give this talk. I have enjoyed these IBiM talks, although I've never actually attended any one of these in person because of clashes with my classes, both in this and the previous semesters. So it's actually a good idea to record these lectures, and I can take a look at them later on YouTube. So just to reiterate my introduction again, so I'm Phanindra Tallapragada. I'm an associate professor in mechanical engineering at Clemson University. My research interests are in the areas of dynamical systems or nonlinear dynamics. I work in several areas in bio-inspired locomotion, unconventional and versatile locomotion, or manipulation problems. I work in areas related to fish-like swimming, low Reynolds number microswimmers, collective motion in the low Reynolds number regime. But I also work in non-holonomic systems, rigid body dynamics, nonlinear oscillations, and so on. So I'll talk about fish-like swimming today and my work in this area, but I'll present a slightly different perspective that combines my other areas of interest. So the usual paradigm in robotics is sense, think, and act. And an overarching theme for my work, just to set a big picture, is to come up with some sort of an alternative paradigm where the sensing is somewhat embodied sensing. So the body itself acts as some sort of a sensor. The think is think little. So by think little, what I mean is minimal computation for decision-making purposes. And the act is more like a reflexive or a reflexive response, or maybe even preflexes, so which have nearly zero delay in terms of like sensing some disturbance and then an immediate action with negligible delays. So I'll talk about passive mechanics in agile turning and swimming and embodied sensing of upstream bodies. These are the specific problems that I want to talk about. But then I want to introduce a novel motivation here for a lot of this research, which is the existence of non-holonomic constraints. And this is motivated by these traditional problems in rigid body dynamics, where there are non-holonomic constraints. I'll talk a little bit about what I mean by that, and then the motivation for swimming. So what do we mean by passive dynamics? So to me, the most well-known example of passive dynamics in locomotion is that of the passive walker. So here I have some pictures of passive walker on the left. I don't have any specific citations. These are very old standard papers. I've just taken some pictures from Andy Luna's lab from Cornell. So these passive dynamic walkers are usually modeled as double or perhaps more inverted pendulums that fall down an inclined plane due to gravity in such a way that the impact of the feet with the ground produce this periodic leg motion. This was once described as brainless and powerless walking. This is not being mean. I think this is more of a compliment because it conveys the idea that a significant component of leg motion requires little or no power and little or no control or computation. So in short, the locomotion / gaits are actually embodied in the physical structure of the passive mechanism. Another example of passive dynamics in terrestrial animals is the role of tails in animals like lizards, geckos, or even other bigger mammals in stabilizing the pitching motion during a jump. So here is a picture on the right from a paper by Robert Full at Berkeley of a lizard performing a jump while its tail stabilizes its ability to land. So lizards with their tails cut off can't jump and land very well. So I only picked this paper because it had a robotic application, and where a toy car with a pendulum-like tail is used to demonstrate the fact that the car can jump off a surface and then land smoothly on a surface that is far away. So, but the question in the case of tails is if they're entirely active or if they have passive dynamics. This is often tricky to answer in situ experiments with animals because nerve activations, measuring nerve activation during motion is difficult. And it's difficult to say whether the deformations of the tail are just passive responses to the motion or whether there is some muscular actuation going on. It's often a combination of both. So of course, there are similar examples in the case of fish-like swimming or fish swimming, and similar questions can be posed. We do not know, or we do know that there are passive dynamics in propulsion in the sense that fish can extract energy from velocity or pressure gradients or from the ambient vortex wake. So in analogy with the passive dynamic walking that we have just described. And so for a motivating example, I'll just refer to a classic experiment going back to the early 2000s, 2006, I think, by Lauder and Triantafylou. So this is I think a reasonably well-known experiment where there is a fish or a trout in this case in a water tunnel. Water is flowing from the left to the right, and there's a stationary obstacle towards the left, and the vortex wake that it produces sucks this dead fish upstream. So in this case, it's a freshly euthanized fish. So it's not actually swimming; it's only moving entirely due to the ambient vortex wake. So in some sense, the efficiency of this fish is infinite because it's actually not using any muscular energy. It's just using the flow dynamics in the water around it. But I also call it attention to the observation that the body of the fish is deforming, and because it's a dead fish, all those deformations are passive. There is no active muscular activation. So in the case of live fish, it's sometimes difficult. And I'll just put some quotes here from papers by Fish and Lauder and Fish and Triantafylou in 2006, where they say that the amplitude of the dead fish motion is somewhat similar to that of a live fish. And although it's uncertain whether this difference is caused by the fish being alive or dead, or just as a result of the mass and size differences, etc. And in a subsequent review paper, they also comment that the extreme bending of fish fins, which is observed in rapid movements, in such extreme bending, it's difficult to delineate or separate what the relative contribution of active versus passive deformations is. So other papers have suggested in the past that passive deformation of the body is initiated in a live fish, and then the animal responds. Once passive deformation is initiated, the animal responds by increasing the rate of deformation. So essentially the computational logic for such swimming animals, it seems, for fish, it seems, is almost that if a deformation is initiated, just increase the deformation. Or if a deformation is initiated, act against the deformation in some other scenarios. So where the motion of the body itself is initially a sensor, and then the body itself is again an actuator. So we decided that the idea of passive deformation or change in shape of a swimmer can help in its motion. We want to test this idea. And we first want to choose a swimmer that can propel itself without any changes in its shape. So we want to come up with some sort of a bio-inspired swimmer that can swim without any active tails or fins. It can still possess some tails and fins, but they should not be actuated. So any deformations of those appendages are then purely passive. And so as to test these ideas of what the role of passive deformations are in terms of. So I'll start, so that sets the stage for what I'm going to describe, but I'll start with a very simple experimental video a very primitive one. I always like showing this video. So what you see in this video is a Szyszkowski foil with a rotor on top of it. That rotor is not in contact with the water. The periodic motion of this rotor, so it's going back and forth sinusoidally. The periodic motion of the rotor produces propulsive motion. Different frequencies and amplitudes of the motion of the rotor can produce different types of motion. I like this video because it's an old video that it's an old setup that we made back 7-8 years ago. And it's an interesting video that I like to show off because it was theoretical ideas in action, basically. So I want to talk a little bit about the motivation for this and how this is now a swimmer without any active tails of fins. This particular model of the swimmer was inspired by a well-known non-holonomic system called the Shipley slate. So I'll now take a short detour to describe the non-holonomic mechanics of the system and how it has played a role in our understanding of these swimming mechanics. So the Shipley sleigh is this cart-like system. So I've shown that on the left figure. It's a cart-like system with a sharp knife edge. So it's a sledge or a sleigh with a sharp knife edge. One other physical system that comes to mind is like a skate with a sharp knife edge. But here I've visualized that, or I've conceptualized that by eliminating the knife edge and using a wheel at the rear end of this system. And it's got casters that allow omnidirectional motion at the front. This is a very well-known system going back to 1908 in the works of Sergei Shaplygin. The configuration manifold, so I'll just quickly describe what I mean by non-holonomic constraints here. The configuration manifold for the system is SE2. It's parameterized by these coordinates x, y, and theta. What that means is that it's parameterized by the coordinates of, say, center of mass x and y and its orientation angle theta. And it's got generalized velocities x dot, y dot, and theta dot. Now we impose a non-holonomic constraint at the rear wheel. What that constraint means, in this case, that's the equation minus x dot sine theta plus y dot cos theta minus a theta dot is 0. What that constraint means is that lateral motion at that wheel is not allowed, but longitudinal motion is allowed. So we have 3 possible velocity vectors, out of which one velocity is not allowed. So the allowable velocity subspace is now 2-dimensional at each q, at each point in the configuration manifold. And that velocity subspace is spanned by these velocity vectors g1 and g2. The Lie bracket of these 2 vectors, g1 and g2, does not lie in the span of g1 and g2 itself. So what that means is that the velocity distribution that is defined by this constraint is non-holonomic. So even though only 2 velocities are allowed at any given point in the configuration manifold, the system itself is not restricted to lie on a 2-dimensional submanifold within this overall bigger configuration manifold. If you have ever parallel parked your car, what you've done is this Lie bracket calculation. The Lie bracket calculation is essentially saying that we'll move in the direction of velocity g1, then in the direction of by small amounts, then in the direction of velocity g2 by a small amount, then back in the direction of negative g1 by a small amount, back in the direction of negative g2 by a small amount. So you move forward, turn your car, come back, turn your car again. And what you have is a net displacement in the lateral direction. So your car is now, therefore, not confined to move along just a 2-dimensional submanifold, but you can hit any xy coordinate and any orientation angle theta. So that's really what we mean by, roughly speaking, what we mean by these non-holonomic constraints. So we want to produce such turning motion on the sleigh. And so to do that, what we imagine is a balanced rotor. We imagine placing this balanced rotor on top of this, and we actuate this balanced rotor periodically. When we do that, here is a simulation of the balanced rotor going back and forth periodically. And when we do that, the Shipley sleigh then moves forward. It's entirely a result of this constraint. So if the non-holonomic constraint was absent, the entire system would just go would spin back and forth in place and would not have any net displacement in one cycle of the motion of the rotor. Here, of course, the example is somewhat artificial. There is no dissipative effect. So as the rotor spins back and forth sinusoidally, the sleigh gains speed, its speed becomes unbounded, and it goes very fast. So later on, in the same problem, we'll introduce some dissipative effects to bound its speed. Now this, we've already seen a physical resemblance between this system and the case of our swimmer, but the resemblance is just more than the physical resemblance. There is, in fact, a nice mathematical similarity between the motion of these two bodies. So I'll now consider, roughly speaking, just a very simplified model of swimming, where I'll analyze the Kataishikowski condition for the shedding of vorticity past an airfoil, or past this hydrofoil in this case. So consider this problem where we have this hydrofoil with the distribution of these point vortices. The Kata condition imposes a constraint on the evolution of the vorticity, or how the vortices, as well as the coupled motion of the vortices, as well as the body is governed, as well as the creation of new vortices. Writing the Kata condition as just saying that at the trailing edge of this foil, the velocity should become 0, where it gives us this equation that's given here as the dw or d zeta equation, where w is the potential function due to the motion of the body, as well as all of the point vortices in the body. So the W1, W2, and W3 are the Kirchhoff potentials, Vx, Vy, and omega are the velocities of the body in its own body frame. And the WV are the potentials induced because of each of the point vortices. So running through some calculations, putting numbers for the parameters of the Tchaikovsky foil, we end up with an equation which is equivalent to the Kata condition as this equation with the minus 2x dot sine theta, 2y dot cos theta, and k theta dot equation, equals minus of uv, which is the velocity that is generated at the trailing edge because of all of the point vortices. Now this equation, this constrained equation, this is a constraint now. This is a constrained equation that is almost the same as the constrained equation that we've seen for the Shipley sleigh, except for the right-hand side, where for the Shipley sleigh, the right-hand side was 0. Here we have perhaps a non-zero velocity minus uv. So we'll just call this the affine Shipley constraint, where for a non-holomorphic system, we can nevertheless prescribe a non-zero velocity. We're still constraining the velocity to be something and not allow it to be a free variable. So this is an affine non-holonomic constraint that is very similar to that of the Shipley sleigh. So new vorticity in these inviscid simulations is created by conserving linear and angular momentum, as well as this Kata condition, which the creation of this new vorticity therefore gives a push to the foil, and the foil can swim purely due to the motion of this internal oscillations of this rotor. So here is a simulation of such a swimmer in an inviscid flow. All these point vortices are inviscid point vortices. There is a yellow rotor placed inside this foil that's executing this sinusoidal motion, and it propels itself forward. Now, if the rotor, instead of executing this back and forth sinusoidal motion, instead of that, if it spins mostly in one direction, so if the rotor spins mostly in one direction, you can get a net change in the orientation or the heading angle of the swimmer. So overall, this becomes an underactuated system where the motion of the rotor can propel the foil forward, and the different motion of the rotor can steer the foil in different directions. And this is somewhat enabled by the existence of this non-holonomic constraint. As I said, non-holonomic constraints enable underactuated systems to access the whole configuration manifold, basically. But as I said, for a real swimmer, there is dissipation, so we cannot just go with the inviscid flow simulations. So first, again, I'll go back to the Shipley sleigh. I'll introduce dissipation into the system. I'll introduce viscous damping, and then apply periodic actuation on the sleigh. And when we do that, the velocity of the sleigh is no longer unbounded. So at the top is a simulation of a sleigh moving forward along the serpentine path. In the bottom panel, you see a figure of the longitudinal velocity u and the angular velocity of the sleigh. So these velocities converge to this figure 8 shaped limit cycle. And given an amplitude and frequency of actuation, there is such a figure 8 limit cycle for the ship-rigging sleigh. Now, in exact analogy for our swimmer, here I'm showing a video of an experimental video of the swimmer, where we measure its velocity, its angular velocity, and we are plotting those variables. What we see is the emergence of this figure 8 limit cycle. So just to clarify, what you see is a swimmer with a board stuck on top of it. The board is not in contact with the water. We are tracking that board with the 2 black circles on it. We're tracking those circles to measure its orientation, to measure the rate of change of its heading angle and so on, as well as the velocity u. So once again, even for a realistic system now, even with realistic damping, there is a nice similarity between this non-holonomic system and the case of a swimmer. That similarity is now at the level of this existence of these limit cycles. Given a periodic input, given a periodic actuation, there is a limit cycle for both of them. Of course, the existence of just these limit cycles in a qualitative sense is nice, but insufficient or not very useful. So we pose some, what I like to call as inverse problems, where we say, given a ship-rigging sleigh, what is the equivalent Minkowski foil with an equivalent actuation that produces the same limit cycle? So what are the parameters of this? What are the shape, mass, inertia parameters of this foil that will produce a limit cycle that is very similar or the same as that of the ship-rigging sleigh, or vice versa? Given a swimming foil with certain shape or inertia parameters, what parameters of the ship-rigging sleigh, what inertia, what mass, and what damping coefficients will produce similar limit cycles? So this question is interesting because we can do calculations with the ship-rigging sleigh. So on the left, my intention is not to go into the details of these calculations. This is just a very quick overview of the kind of calculations that we can do. So on the left, we have these 2 equations. These are what I call as the reduced velocity equations for the ship-rigging sleigh. We can derive them analytically. And then we can find solutions to these equations for the case where we have periodic inputs like A cosine omega t, which is due to the actuation of that rotor. We can do a harmonic balance calculation for the approximation of limit cycles. We can match coefficients, or we can find out coefficients by matching the different frequency components, and find an expression or find an equation for that limit cycle. So in this figure on the bottom, I've shown the limit cycle in red. The red dashed line is the limit cycle for a ship-rigging sleigh, which is an analytical calculation. Now we can do a least squares estimation for the parameters of the foil, which produce a similar limit cycle. So that limit cycle I've shown in this blue curve. So we can produce a one-to-one. I use that one-to-one somewhat loosely. So they could be more than one foil. They could be more than one ship-rigging sleigh, which produces similar dynamics to that of the foil. But we want to identify at least one such ship-rigging sleigh system whose dynamics would be very similar to the Minkowski foil, so that we can first come up with a control scheme for the ship-rigging sleigh, which is governed by these simple equations, and then see if the same control scheme would work for a swimming body. So what works for the ship-rigging sleigh works for the swimming foil as well. So here is a simulation where what we do is we do velocity tracking. We prescribe a velocity that the sleigh should move at, and then we also prescribe that it should move along a straight line, and then after some point it should make a turn and go along a different straight line. So we're doing velocity tracking and steering of the ship-rigging sleigh. Whatever control input that we come up with, and we came up with this control input by doing averaged proportional control, the same control input works for the swimming foil, at least in our simulation. So on the right, what I'm showing is the longitudinal velocity of the sleigh and the foil. For the sleigh, it is in the red dashed line. The blue line is for the foil. Here we are showing on the figure on the left, we are showing the heading angle. So we wanted to move along a straight line, a horizontal straight line, then make a quick transition to a vertical straight line. while always tracking their desired speed. And we can vary this desired speed. Basically, what we're doing is tracking limit cycles in a velocity space and tracking a path in the actual physical space. So that gives us this velocity tracking as well as simultaneous path tracking. Here, I've only shown the steering problem. There is quite a bit more that we can do with this, with the similarity between these two systems. So maybe I'll be back next year talking about reinforcement learning problems, where we control a Shapley sleigh and then apply a similar algorithm as a starting point for the path tracking or path planning of a swimmer in experiments. But for now, I'll stop with this analogy here and then move on to the role of passive dynamics and the turning motion of the swimmer. So here the turning motion actually occurred with a significant turning radius. And we want to see what the role of the passive dynamics is in enabling faster turns. So to that end, I'll go back to an experimental video because what we saw was just simulations. So here is an experiment where the foil tries to make a turn. First, initially, it's gaining some speed, and then it tries to make a turn of about 90 degrees. And the turn is produced by spinning the rotor very quickly in one direction without the back and forth motion. So lighting in this is not very good, but that was somewhat intentional. What we were trying to do, also, I'll play this movie again. What we're also trying to do is capture the shadows of those nearly discrete vortex structures. You can see some shadows in the water or on the floor of the pool. These are actually the centers of the vorticity that is being shed. They have a fairly discrete structure, at least for some short time scales before they diffuse away. So the swimmer's ability to make quick turns is actually not that great. It is able to turn, but it takes some time to make these turns. So next, what we want to do, because we have this nice platform, without any tails, without any fins, we can test out these ideas of what happens if we have passive tails. So this picture shows on the top, this picture shows the swimmer with a passive tail. So the joint is not actuated. There's no motor or anything that's driving the joint. The motion of the joint is then purely going to be because of whatever the motion of the water around it is going to determine. Again, and without getting into details about this, again, this is partly inspired by the turning motion of a Shapley sleigh with a passive tail. So we impose a constraint on the tail, but no constraint on the main body. And we'll see that the turning motion of the Shapley sleigh is increased if the center of mass of if the line joining the center of mass of the Shapley sleigh with the constraint point doesn't align with the longitudinal allowable velocity direction. So roughly what happens is that with different periodic inputs or with different types of inputs, the sleigh's velocity gets pushed away from the limit cycle, and that limit cycle becomes unstable, basically. So the sleigh doesn't return easily, or the sleigh's velocity doesn't easily return to the limit cycle because it is now unstable. So a disturbance then changes the stable configuration of the sleigh, makes the tail turn, and the turning motion of the tail then produces a very quick turn of the overall body itself, which is what we're going to see with the actual swimmer as well. So here are two videos of two foils. One of them has this passive tail that is shown with this orange color in the left panel, and one of in the right panel we have this foil, the swimming foil, which is just a rigid body which doesn't have any passive tails. We'll apply the same exact control inputs, which means that we'll apply the same rotor velocities on both of them, and we want to see how well each of them can turn. So on the left, what we're showing is sinusoidal control input to give the foil some initial velocity. And on the right, we are seeing the heading angle of the two systems, of the two foils. So when the rotor spins in the same direction at a continuous rate, the body with the passive tail makes a larger and larger turn. So the total change in the angle, in the heading angle of the foil with the passive tail is larger. I'm just going to play this again. The control inputs in both the cases are exactly the same. And that's the control input that's being shown here. So now the rotor turns constantly at a constant rate. And the angle that the body with the passive tail turns is more than the angle that the body without the passive tail turns. And this keeps repeating as the same motion is executed again and again. So we want to see what further, if we can further see further gains in the turning ability by adding more of these passive tails. So in the previous example, the rotation of the passive tail was constrained by how much it could turn. So once it achieves a certain turn angle, the tail segment collides with the main body and then can't turn any further. So here we allow a greater range of motion, as well as we actually have two segments for the passive tail. And so now making the rotor turn in one direction enables a faster turn, enables a turn with a smaller radius of turning as well. And that's the movie that shows that. So here is a side-by-side comparison of different foils with different types of passive tails. Our intention here was only to test what the role of the range of motion of the passive tails was. It was not really a test of the different geometries of the passive tails themselves. Essentially, what we observe is that a body without a passive tail. So in all the cases, the actuation is exactly the same. The same amount of torque is applied in all of the 4 cases. So without a passive tail, the body takes a fairly large amount of time to make about a 90-degree turn. The first 60 degrees or 70 degrees is fast, but after that, the angular velocity slowly decays or decays very quickly. And then the foil doesn't turn all that much. So the first 60 or 70 degrees for the rigid body can be achieved in about 2 or 3 seconds. But thereafter, the turning motion slows down. On the other hand, in the extreme case where we have passive tails that can have a high degree of rotation. So that high degree of rotation is enabled actually by the existence of the second segment, which can turn quite a bit. We can get the robot to turn about 100 degrees, 90 degrees to 100 degrees in less than a second. And then about a full 180 degrees in about 3 seconds, 3 to 4 seconds. The radius of turning is also just about half a body length or less for a 180-degree turn. So which is quite an improvement compared to the case of just the rigid body. So here is a demonstration, then going back to this comment that that was made in the paper by Fish and Lauder about it's difficult to ascertain how much of the deformation of the fins is active versus passive and what role they play in the turning motion of a fish. Well, here is an experiment where we have this body where all of the deformations of the tails are entirely passive. So there's no active component to it. And the passive component, just the passive deformation, makes a very big difference to the turning ability of the swimmer. Now, I'll just analyze what the role of this passive deformation is with some further calculations for the simulations. But first, I'll make a few quick observations. So when we have this body with the passive tails, what we see just looking in the pictures of the experiment is that as the main body turns, for instance, in this case, in the clockwise direction in this left panel here, the tail counter-rotates in the counterclockwise direction. After a certain while, when the body reaches its mean position, so as it's going back and forth and the rotor spins in the other direction, when the body is rotating in the counterclockwise direction, the tail now goes in the clockwise direction. After a certain while, of course, they both, again, there is a certain part of the motion where they're both rotating in the same or turning in the same direction. I've not shown that in this picture. I'll show that in the later picture. So this provides us some insight into a rough explanation for what is going on. So I'll go back to this Kutaishkovsky condition and say that if the body is turning in the clockwise direction, so the body's angular velocity is shown by this capital omega in this panel here in the right panel, figure A, the vorticity that has to be shared to preserve the cutter condition, roughly speaking, has to be in the counterclockwise direction. That's shown by this blue spiral here. That's because the trailing edge will have a velocity shown by this blue arrow, Vt, and to maintain zero relative velocity, the vorticity has to be in the counterclockwise direction. If we do a calculation for what the hydrodynamic moment that is exerted by this vorticity is, that hydrodynamic moment is shown by this term mv that opposes the turning motion. Now, if we take the case of a body with a tail, and if the tail's angular velocity is such that it is in the opposite direction, so that's shown by this omega subscript t, the trailing edge can have a velocity vt, which is in the opposite direction. That depends, in fact, on the relative magnitudes of the overall angular velocity omega, the angular velocity omega t, as well as the body velocities vx and vy. But it's quite possible to have a velocity at the trailing edge, which is in the direction shown by that red arrow. And again, roughly speaking, the kata condition then creates vorticity that is in the clockwise direction. That's shown by this red spiral. Now, calculation of the hydrodynamic moment by such vorticity will produce a moment that is in the same direction as the turning motion of the body. So in case A, I'll call that opposing moment. In case B, I'll call that an aiding moment. So that's a helpful moment, which can help the body turn very quickly. So this is just a rough calculation or a rough explanation, a back of the envelope sort of calculation. And I'll just verify, we verified that with some computations. And we use the panel method for these computations. So here is a quick description of the sort of computation that we did. We use the unsteady kata condition now. That's given by this equation on the second line. We compute pressure on each panel using the unsteady Bernoulli equation, and then compute the hydrodynamic moment because of the vorticity that is created. There is also viscous dissipative effects in the system that we introduce. And doing that, here is a simulation of two foils. I'll just stop the simulation. The foil on the top, the tail is rigid. So even though it shows the body with the tail is rigidly locked. We impose a locking condition so that it acts like one rigid body. While for the foil on the bottom, the tail is allowed to move. So we are applying once again, the same periodic input in a free stream velocity, which are all the same for both of them. There are two different simulations. I'm just showing side by side. So there's no hydrodynamic interaction between the two bodies. I will zoom in close to the trailing edge into this movie and then point out that the sign of the vorticity that is created at the tail is different. The tail, in fact, has a different phase in its motion compared to the trailing edge for the rigid one. So roughly summarizing different snapshots of the simulation on the right, there are phases within the motion of these two bodies where the sign of the vorticity that is created at the trailing edge is the same for both the bodies. That would be figures B, or the second row of the figures in both of these panels, as well as the last row of the figures in both of these panels. But there is also a certain part of a certain phase of the motion where the sign of the vorticity is different. So that would be the top row and the third row, where you can see just by the color difference in the vorticity that the vortex sign is different. So I've introduced the term gamma here, and I've indicated what the sign of the vorticity is, and shows that the vorticity is of a different sign for at least part of the motion of the two bodies. So we then compute what the hydrodynamic moment that is created by all of the vortex vectors, not just by the vorticity that is being shed at the trailing edge, but by all of the wake that has already been created. So in the top panel, in the top row in these two graphs show the hydrodynamic moment that is exerted by the vortex wake on the body, as well as the sign of the vorticity that is being shed right at that instant at the trailing edge. The blue region here is the hydrodynamic moment that is favorable to turning, that is in the same direction as the turning motion of the body. The red dotted line or the dashed line that I plot here is the angular velocity of the body as it is being forced to do these oscillations. So when those two signs match, we call that as a favorable hydrodynamic moment. So from this figure, we can see that for the most part, for the body without any passive tails, the movement that is exerted by the vorticity is unfavorable. It is opposing the motion of the, is opposing this turning motion of the body. While for the body with a passive tail, the movement that is exerted by the vortex wake is aiding the motion, or it is favorable to motion for about half the cycle, actually, for half the cycle of the turning motion. So therefore, the resistance that it encounters to turning is actually fairly small. And all of this is enabled just by the existence of that passive tail. We're not doing anything that is different between in terms of the actuation for both the bodies. The tail is not any smart tail. There is no other further control input on the tail. So that in some sense, actually, what this does is, again, I go back to this problem of what is the role of passive dynamics, or what is the role of passive tails in turning. We think that with these types of swimmers that are driven by these internal rotors, we can conclusively show that passive tails play a very significant component in the turning motion. So we're not combining anything with the active motion. We could do the following trick of, if the tail begins to turn in some direction, turn it faster. So we use the tails for feedback and then actuate the tail. So that's perhaps what fish do, but we've only explored what the role of the passive mechanics are. Now I want to move on to the part of the talk related to sensing, which is the embodied sensing part. So here is a picture from Wikipedia of the lateral line sensors of a fish. I think everyone knows here what we're talking about the lateral line. These are small hair cells or hair-like cilia-like cells on the fish that respond to velocity and pressure gradients, and their motion is transduced to electrical signals that tell the fish something about the ambient flow. And it's well known in several papers going back to, in fact, I think the 1970s or 80s, where it's been shown that blind fish can school, but fish without lateral lines cannot, or blind fish without lateral lines cannot. So that's indicative that lateral line helps a fish build a non-visual picture of its surroundings. So it helps detect predators, prey, obstacles, and so on. We want to see, I'll just say a little bit more. So less well known is that some fish also use fins as sensors, as mechanosensors. So fins are proprioceptive. The rate of bending of fins encodes information. And we want to see if such proprioception can be used to detect predators or prey, or in general obstacles, or something about the upstream flow. Lateral lines, so the difference here is that lateral lines are specialized sensors, but proprioceptive sensing, in the case of a robot, only requires that we measure kinematics. So this would be accelerations and velocities of the swimmer itself, or accelerations and velocities of appendages of tails or fins on a swimmer, which is much easier, which is much cheaper. So we'll use a similar setup to explore this ability of a swimmer to use proprioceptive sensing to identify what is in front of it or what is upstream. So I'll call this a blind fish in a water tunnel experiment. What we have are two hydrofoils, two Zhikovsky foils. The trailing foil is shown, is a passive foil. It is tethered by a very short string, by a very short wire to this rod here. And its motion is entirely determined by the motion of the water in the water tunnel. Upstream, what we have is another foil. So we've, once again, placed these boards on top of these foils. These boards are actually not submerged in the water. These boards are there just to enable us to track the motion of these bodies. So upstream, we have one more foil, which is forced to oscillate sinusoidally. So here is a schematic picture. The upstream foil is oscillating periodically. There is a free stream velocity u infinity, and the downstream foil is going to respond. Its motion is entirely determined by the free stream velocity as well as the oscillations of the upstream body. So here is in this picture, we've captured a shadow of this of the vortex wake that's being created. We want to see how the vortex wake influences the motion of this body, and if the motion of this body, of the trailing body, can be used as sensory information to identify the upstream dynamics. So we're going to do this identification problem in terms of the Struhel number of the flow. So here is a video of such an experiment. So the upstream foil is being actuated periodically, and the downstream foil just responds to the motion of the water around it. The die just shows the creation of the, or shows the vortex wake that the downstream foil is experiencing. So we've done these experiments with different forcing amplitudes, different forcing frequencies, different free stream velocities, and put them together in wake classes. So we assign these class labels. We'll assign these class labels by the Struhel number. So in our experiments, the Struhel number ranges from about 0.21 to about 0.45. So this is the range in which many aquatic animals swim. So what we do is we do these experiments and collect these videos, which are usually about 15 minutes long. We then, well, before I further explain the processing steps, I want to emphasize that the vortex wake can be fairly complicated. We considered cases where the amplitude of oscillations of the upstream foil is large, as well as the velocity, the free stream velocity is small. So what that does is that the vortex wake that's created, we'll imagine that as if it's anchored by these point vortices, but of course the wake is both advected and it is also diffusing. So it diffuses sufficiently before reaching the downstream foil such that it collides with the walls of the water tunnel. So in some of these experiments, there is significant interference in the vortex wake from the boundaries of the water tunnel, while in some of these, that interference is smaller. So the vortex wake doesn't diffuse sufficiently enough. Most of it, it doesn't diffuse sufficiently enough. And what downstream foil experiences is mostly the effects of just the upstream foil without the effects of the boundary changing the vortex wake. So we've considered both such classes in our experiments to make to at least consider some of the vortex wakes that could be more realistic or more emulative of vortex wakes that may be experienced in a realistic environment. So what we do is basically we are plotting here the angular velocity of the leading foil and the angular velocity of the trailing foil. I just want to show that we can't easily do this identification problem just by looking at the frequency components in the velocity of the trailing foil. The frequency, just doing the Fourier transform and doing a power spectrum for the angular velocity of the trailing foil shows that there aren't necessarily obvious patterns that we can use here to say if the trailing foil has the following frequency, the upstream foil has to be doing the following Struhel number kind of calculation. So I'll, in the interest of time, I'll skip this analysis to say why just straightforward harmonics are not very useful. What we do is basically take the angular velocity of the trailing foil. We cut that into different snapshots, each snapshot being 1 second in length to up to 4 seconds in length. So we've tried different things. We rescale those angular velocity signals so as to eliminate the effect of the distance between the two of them. And the rescaling is shown by this equation here. So we are in some sense normalizing what the angular velocity of the trailing foil is. We shuffle the snapshots and then feed those snapshots to a neural network, to a classifier, basically. This is a fairly shallow network. Again, without, I think I'll skip the details of the neural network here. It's a fairly shallow network. We have about 80% of the data as training data, 10% is validation, 10% is test data. And the output of the network is a probability vector that assigns the probability. So it's got 16 components. Each of the components is a probability that the wake that the trailing foil is experiencing belongs to one of those 16 classes. The training for the neural network is through stochastic gradient descent. We use early stopping to prevent overtraining for the network. And we've trained several different networks, varying different parameters, different number of layers between the different number of layers, different number of nodes in each layer, and so on, and then identified what we thought of as a best network. And I'm only going to describe the results corresponding to the good networks or one of the better networks. So here is a confusion matrix that describes the classification accuracy. And what we see is that the classification accuracy is actually pretty good. It can be as high as 0.98, which is about 98%. The worst case accuracy is about 0.7, 0.73. It's about 73%. And the poor accuracy are for wakes where we observe. So for example, here, vortex wake 16 is poorly classified by the downstream foil. Its classification has an accuracy of about 0.73. And wake 16 is one of those wakes where there are significant wall effects in the vortex wake that the trailing foil or the downstream foil experiences. So the vortex wake diffuses sufficiently, collides with the walls, and then the wall effects are then embedded into that information that the trailing foil is experiencing. Where such effects are small or non-existent, the classification accuracy is extremely high. So the classification here, I'll just emphasize, is based upon angular velocity inputs. So here we've shown what the classification accuracy as a function of the length of the snapshot. So when the length of the snapshot is 1 second, what that means is that we are using about just 1 second of the information. The fish needs to use only 1 second of the information and then decide what is upstream in front of it. Versus when we use delta t is equal to 4, the fish can use 4 seconds of the information and then decide what is upstream of it. So the classification accuracy for these 1 second snapshots is actually not that good. It's about 60 to 70% in the best case scenario. But the classification accuracy takes a big jump the moment we use snapshots that are about 2 or 3 seconds long. In terms of body lengths, that a swimmer would travel, so using the free stream velocity as a scaling factor, a 2 or 3 second snapshot would correspond to about, roughly speaking, about 2 to 3 body lengths. So as the swimmer is traveling, if it travels about 2 to 3 body lengths and then uses the angular acceleration of, say, its tail for that period of time, it can classify what is upstream of it quite well. That's where we are trying to push a conclusion towards. So at this point, this is still an experiment in a water tunnel. As I said, maybe next year I'll be back with more realistic experiments of an actual robot doing this for obstacles that it experiences in front of it. In the grand picture, what we want to do is, going back to what I started off with, we want to use this sort of embodied sensing. So we can have robots with passive tails whose angular motion tells the robot something about what is in front of it, predators, prey, obstacles, etc. And then the same tail can be actuated if necessary. So it's both a sensor and an actuator. And the motion of the tail is like a preflex or a reflex that immediately sets off a control input that tells the tail to do something without any further computation or without any further decision making. If the tail moves in a certain manner, we pick off a certain response for the tail, and the robot can either avoid an obstacle or either avoid a predator, or perhaps if what is upstream is a prey, it wants to go and catch that prey by redirecting or re-steering itself towards the prey. That's really where we are going at. But what I presented today are a few what I like to think of as canonical problems that highlight the role of passive dynamics, passive degrees of motion, in both improving the agility as well as in improving the sensing capabilities of an underwater swimmer. And I've also made a connection with terrestrial non-holonomic systems, which are easier to analyze, so that we can try out some control algorithms on those systems and use that as a starting point for swimming robots. I'll stop here. I'll take questions. Just a moment, I want to acknowledge this work has been funded by 2 NSF grants primarily. A lot of this work has been done by my 3 graduate students, Bo Pollard, Vitaly Fedoniuk, and Colin Rodwell. Bo and Vitaly have graduated their postdocs at CMU now. Colin is my current PhD student who's working on these projects. I am looking for graduate students and postdocs. So if anyone is interested, please send me an email.
Okay, let's thank Professor Phanindra Tallapragada for his interesting talk. And anyone have any questions?
Yes.
Tisha.
I actually have a lot of questions, Phanindra. So, like, first of all, first comment, like, if you have like advertisement want to advertise, like, we can put in our, like, again, like, in our IBiM. I know we have done this, like, but we can put it out again to, like, remind every people, like, there's, like, terrific opportunity for working with you, like, to the mailing list. So anyway, going back to, like, I really like the simple, like, abstract model for this passive, like, swimmer. Like, it reminds me of, like, a cubulus, like, this, like, a magic cube can stand up using, like, like a eccentric, like, the torque. So, but going back to the, like, first, like, slide of your motivation, which is the passive worker. So from my perspective, like, from passive worker is, like, there's 3 key components to that. One is the initial condition. They need initial push slightly. And then there's also, like, this, like, slope, which is, like, the gravitational effect. And the third is the, like, this, the magical part from my perspective. Like, the magic part, like, I heard, I have been, like, follow up is they actually tune very carefully the suction cap of their knee. So in the way that this knee cap, like, kinematic dynamics will really determine whether you can start walking or just fall off, or, like, this. So with that being said, for the, like, a knee suction cap, so basically what they change is, like, to some degree is the stiffness and, like, the damping. So in your case, the tail, are you planning to explore, or have you already explored, let's say the tail is actually have a little bit, like, different stiffness? Like, so basically also, like, in nature, we have see, like, for tuna fish or this, I think there's a new publication in Science Robotics that the tail itself is, like, they can change stiffness a little bit. So in the way to work optimally, like, in different, like, swimming regime. So this is the first question, like, I want to, like, ask from you. So.
Okay. Yes, we have considered that problem of can we change the tail stiffness and then get different gaits, different types of motion. So the gaits here have different efficiency. So if the tail oscillates too much, the body surge velocity can be large, but it does a very serpentine path and its net displacement along a line would be small. So in some sense, its efficiency drops. So the tail stiffness does determine the efficiency of the motion. But more importantly, more interestingly, tail stiffness can induce faster turns. So if the tail is very stiff, it's essentially a rigid body, right? So, but in that case, actually, we can get slightly faster swimming speeds with just this experimental platform. And if the tail is flexible, the swimming speeds are somewhat smaller. The difference is actually not that much, but it is there. It is there consistently in several experiments. So, but a flexible tail will enable the body to turn faster. So we've explored this idea of can we have a single stiffness, because changing the stiffness can be difficult, or can we have a single stiffness, or can we have a single spring? I won't say a single stiffness, but a single spring which is non-linear, right? So something like a Duffing oscillator type of a spring with multi-stable potentials. But the Duffing oscillator, obviously the mean position is unstable, but we're considering like higher potentials where the mean position is stable and there are two further stable positions, right? So I didn't talk about that work here. That work is still in progress. We recently just had a paper accepted in nonlinear dynamics on this problem in the context of the Shepley-Ginsley. So we first tried this in the Shepley-Ginsley where we show without changing anything else about the stiffness parameters, without changing anything about a physical spring. Because it's a nonlinear system, its dynamics have a frequency and amplitude dependence on the actuation. It's not just a frequency dependence. So by having different frequencies and amplitudes, we can get this limit cycle oscillations of the tail about its zero mean position, or by hitting a different amplitude and different frequency, there is a bifurcation, the limit cycle becomes unstable, and we can push the tail with a very small disturbance to a different position, and the tail oscillates in that along that different equilibrium. So we call this like, and in this case, we only consider just a hook type of a spring. The spring itself doesn't have any multi-stable effects. All the multi-stable effects are induced by the non-holonomic constraint. So there is an effective potential that is created by the constraint, which creates this effect where we can choose a limit cycle. We can choose which limit cycle to make stable by choosing our forcing frequency and amplitude, and we can switch between these limit cycles. So that produces straight line motion versus motion along a circular path. So the circular path is we can piece together these curves to produce curved motion, basically, or very fast turning motion. Yep. So we are yet to explore that same thing with an experiment in swimming, but yes, that's where we want to go.
Yeah. So like a continual question, like maybe even more people, things get complicated. A little bit of background is that there's a lot of people like working on swimming robotics right now. It's a purely soft robotics. Mm-hmm. And in your case, I think you demonstrated is like at least a 3 linkage of rigid body. Mm-hmm. Is like, very like, can also demonstrate like a very interesting like, behavior of like, fish. Mm-hmm. From my perspective, like going extremely soft or extremely rigid, like there are force diagonally. So like there can be like a combination of like together. It's like we can say flexible, not a rigid or soft. So, but there's still like this limitation per se. How you see, if I can ask a little bit philosophical question, like these two, like both material wise as well as like the softer material and as well as like this rigid, like can combine together or meeting to some degree in the middle ground. Maybe just a little bit like a more like a futuristic or like a more like a difficult like a question to answer, like or maybe like it's not well defined a question, to be honest. But like I just want to get your like perspective on this.
So at least superficially, I can think of it as a rigid skeleton and let's say a soft polymer body around the rigid skeleton. So what we are demonstrating could be the rigid skeleton inside that is encased in a soft body, and the motion of this rigid body then produces the motion of the softer body around it. That's my superficial answer. But I also like to think of it in terms of nonlinear dynamics. So I want to think about what the effect of the softer body is in terms of a potential function, and so in terms of potential function with multiple equilibrium positions, perhaps, or nonlinear effects. So it's not just a quadratic potential, but it's a more interesting potential function. But at that point, it's also, I think, complicated enough that we can have tunable effective potentials.
Yes.
Right? So the tunability is primarily because of just this control inputs. The effective potential, we're not changing by changing the material parameters each time we take one set of material parameters, but we can change their effective properties by the frequency amplitude of the inputs.
I just want to like a comment down on that. Like I completely agree on this. Like so, from my perspective, the rigidness, like just like a fish, have like their spine. They have like still like rigid part. Like, but on the other hand, the meat, other things, well, they use as the actuation, but also like from my perspective, like it's a tuning property. It's able to tune the like say like the distribution of mass. There's also like the like stiffness, also maybe damping. So which like to some degree, like for the like the beautiful nature have shown for this rainbow trout is that they actually design in a way that like a mass and the like stiffness and also like even like other characters have been like carefully designed by nature. So in the way when there's like unsteady potential or unsteady like external force, which is like the common vortex street coming, is able to slamming through this, and just like the passive worker taking advantage of the like the gravity. So that's I see like a joint like marriage like between like a rigid and like soft become a flexible, like, body. I just want to, like, I really like the work.
So my research interests are in nonlinear dynamics, actually. That's my primary area of interest. I just pick different problems from different areas where there are interesting nonlinear dynamics going on. So one of the things that we've done, and that's obviously not in this talk, is make these soft, hard robots. So a combination of a hard shell with some soft cilia, soft bristles that can climb, that can crawl on vertical, that can crawl on horizontal surfaces and climb pipes or vertical surfaces, purely because of such periodic inputs. We have just a periodic rotor that's turning inside. These are fairly small, fairly light robots weighing about 20 grams. And it's a similar effect that we are exploiting there. In fact, because obviously without the fluid structure interaction, we can come up with good analytical models. There we actually showed that it is a Matthew oscillator. And what we're doing is hitting different resonance ranges. Each of the resonance bands produces different types of motion. And it's very tunable. At that point, you can change the frequency of the oscillations of a motor. These are small vibrational motors that can achieve very large frequency ranges and get very different types of gates. You can get a body to move forward, backward, just by changing the frequency, make it turn, make it climb up a surface, and so on. We obviously want to try some of those ideas with swimming robots, but the analysis becomes harder and harder as we go along. Simplified models are harder.
Yes. Thank you. Thanks, Li Jun, for just allowing me to ask that much questions. So,
thanks for the good questions,
Okay.
interesting questions.
Okay, any other questions? Okay, shall we stop here? And thank Professor again for his excellent presentation, and thank everyone for attending today's seminar. So,
Thank you very much.
Okay.
Thank you.
Thank you very much. That was fantastic. Take care.
Happy Thanksgiving. So
Happy Thanksgiving, everyone.
Okay. Bye.